next problem is called least recently used cache. They basically have to design a data structure that follows the constraint of the least recently used cache. We have to implement that class. Basically, we'll have the constructor of the LRU cache, and the constructor will initialize the cache with positive size capacity. So we'll be given the capacity for our cache in the constructor as parameter to the constructor, and then we will have two methods as in any cache. We'll have the get, which will basically check if we have the key passed as the parameter to the get function in our cache and return the corresponding value. If that key doesn't exist, then we will just return -1. For the put function, we will be getting a pair, basically key and the value, and we will update the value of the key if the key exists. Otherwise, we will have to add the key value pair to the cache. But then the special constraint for the least recently used cache is if the number of keys exceeds the capacity from after we have, for example, added a new key value pair, we have to evict the last recently used key. And the functions get and put must each run in a linear, basically in a constant average time complexity, because in a regular, for example, hash map, we have a constant average time complexity for both get and put. Now, the first hint when we are talking about cache should be the hash map, because hash map, as we said, it enables us to get the to store the key in a average constant time complexity, and also to retrieve that key, to retrieve the value mapping to that key in the same constant average time complexity. So that basically is enough for us to implement the get and put functionalities. But now the thing is that we had this eviction of the last recently used keys, and basically eviction is just a removal from the from our cache, and there is no well in the basic hash map in, for example, Java, there is no eviction based on the last recently used key. So we will have to implement it in using another data structure. An array wouldn't be a good option for this, because in eviction is basically removal, and in the array, if we have an array, for example, of 3 or 4 elements, if you want to evict or delete the second element after its removal, the elements after it will be pushed basically to that space. So we will not really have a constant time complexity for the eviction, and because we don't have the constant time complexity for the eviction, we will not have the constant time complexity for the put method, like the total time complexity required for the put method as well. So this happens because the array is a continuous data structure. In memory, is basically a block per block per block, block after block after block. Another data structure that enables us to freely move the elements however we want is a linked list. Basically, in the linked list, the specific nodes don't have to be next to each other. So if we have 2 nodes, these nodes can be in a completely different space in the memory. But because we have this next pointer, we can traverse through the linked list. Now, because we also need we will be removing elements from, basically it can be the head element, the tail element, any element in between, it's also useful to have a double linked list. And in a double linked list, instead of having just the next pointer, so that's basically the regular single linked list, in the double linked list, we will also have the previous pointer. So one's next pointer will be pointing to 2, and the 2 previous pointer will be pointing to 1. So basically, if you are at the element 2, we can use the previous pointer to remove the element 1. And if we are at the element 1, we can remove the node 2, because we have the next pointer. So basically, the least recently used cache is implemented by using the federation of data structures, and the data structures that are being used in that federation are the hash map and the double linked list. And we'll see on an example how we are going to use these two data structure. So basically, by the problem statement, we'll receive the capacity for our hash map in the constructor, and because we will have a double linked list, we will create two artificial sentinel or dummy nodes. We will call them head. So this is basically our head and tail. And they can have artificial value, for example, -1. It doesn't really matter. And so this will be the first thing. And we will also connect the heads next to tail and the tails previous to head. So they are we have a doubly linked list using only two artificial linked list nodes. So that's the first thing. Then we basically that's the linked list, and for the hash map, we will just have a regular hash map in the, for example, Java programming language. So these are the two this structure we have, and we will also initialize our capacity. So now on the get, we now have to implement the get and put functions. On the get function, we will basically check if we have a key inside our hash map, and then we will retrieve that. Key value pair, for example. But let's first input, like put some nodes in the linked list. So let's just say we are first calling the linked list with put 1 and 1. So basically, we will get the reference to the we'll basically first check if the value exists in the hash map, and let's say it in this case it doesn't. So we will have to create a new node that corresponds to that key value pair. So we will create that node, and we will have to add it to the list. So we add it by using the reference to the head. So let's just say we will have a function called add to the head. So because when we are adding a new node, that node with that certain key is currently the most recently used key. So we have to move it to the front of the head. Because we didn't mention, but for the eviction, we will basically evict in the opposite direction. We will evict elements that are that tail is currently pointing to, because those elements will be the elements that are those keys will be the keys that are least recently used. So basically, if a node is closer to head, that means it has been used more recently, and if the node is closer to tail, that means that the node hasn't been used recently. So we will have this method add to the head, which will basically do the following. So first we will create a new node. Let's just say it's the value 1 with the value 1, and we will also declare the key. And we will see in a moment why do we need the key as well, and not only the value. So we will have the key value pair, and now we have to connect it inside our linked list. So how do we do that? First, we will point to whatever heads next is pointing to, because we have to connect this node to the rest of the linked list. So if we had nodes that are connected to the head, in this case we have an empty list, basically only two artificial head and tail linked list nodes. So basically in this case, this new node will be pointing to the tail. So that's the first thing that we have to do. Then we have to make the element that was before closest to the head. Its previous relation has to point to this current node, because this node will be before it. So for example, if we had a node here, we would have to change the direction of the previous relation for this to point at this our new node. But in this case, because head's next element is tail, we will just change this direction here. So tail will not be tail's previous pointer will not be pointing to head anymore, but it will be pointing to the new node. Okay, after that's done, we will redirect the head's next pointer to point not to the tail, but to the node, because that's now the closest element that we have in our linked list. And then the last thing that we have to do, we basically have this head next relation, and we have the nodes next relation, and the basically tails previous relation. The only missing one is the previous relation for the new node. And the new node's previous relation, when added to the linked list, will always point to the head, because that's now the closest element that we have to head. So after the node has been added, we will basically have our head node. Head node will be pointing to that new node with the value 1, key value pair 1 and 1. And next pointer for our newly added linked list node will point to tail. Next, tail previous will point to this element, 1 and 1, to the newly added element. And previous connection for the newly added node will point to the head. So because we have both of the next and previous relation between the three nodes, we know that we have a complete list, and we can say that the new node has been added. We will also just increment, for example, the number of nodes that we have in the linked list to keep track if that number is larger than the capacity. So in this case, it will be just 1 because we just added only one element. Next thing that we have to do is because of fast retrieval, we have to put the key value pair inside our hash map. So we'll basically map the key 1 to the value 1 in our hash map. So next time when we add, for example, the element 2 and 2, that element will now become the most recently used element. So we will just call this add to head one more time, and basically do the reconnection. In that case, the head will be pointing to the 2, 2 previous will be pointing to head, 2 next will be pointing to 1, and 2 previous will be pointing to 2, and the same relation for the 1 and 1 connecting to the tail. So 1 will be pointing, 1's next relation will be pointing to tail, and 1 tail's previous relation will be pointing to 1. So again, we have a complete linked list. Next time when we add a new element, let's say we had our capacity set to 2. When we add a new element, let's just say 3 and 3, we know that we have to evict one number. And to evict a number, we will basically just have a remove node function, and the remove node function we will basically just use it to find that node. And once we get the reference to the node, in this case the least recently used is the node with the key 1 on 1 in the second example, because we just added 2. So when we are adding 3, the least recently used node is the one with the key value pair 1 and 1. So to remove this node, there are only 2 things that we have to do. The first, basically, to the redirections of the next and previous relation. So if we have, let's say, the node is this one, we can use the previous relation pointing to the element 2 and redirect the next relation of the node with the value 2 to point to our next element. So in essence, we are doing this. We are first getting the previous element, which is 2, and then we are redirecting its next pointer to point to whatever our element after the element that you are trying to remove is. So in this case, it will be tail, but basically we have this reference node next, which is pointed to the next element. So in this case, we will be changing this relation to not point to 1, but to point to the tail. And then the second thing that we had to do is use the node next, which in this case is tail, and use its previous relation to redirect it to not point at our current element, but point to the node basically element before it, because we are using this relation here. So tail will not be pointing to 1 anymore, it will be pointing to 2. And basically in this case now 2 is pointing to tail with the next relation, and tail is pointing to 2 with the previous relation, and we have removed this node. And we will also remove it from the from our hash map as well. So that will happen when we have to evict one node before adding it. Now the only scenario that we haven't gone through is when we are getting the element and also updating existing key. So if an element exists inside if a node with a certain key exists in the linked list, we have to update it. But before we update it, basically we have to move it to the beginning of the linked list, closer to the head, because it was the most recently used one. We just changed its value. So to do that, we will just use the remove node to completely remove it from the linked list, and then we will just add it again to the head, just as we did for the nodes that we are just adding. Basically, we didn't have before that key and value mapping, and we are adding them for the first time. It goes to the same for the update. We'll first remove it, and then we will add it. We'll add it again. Now for getting the key, we will basically check if that key exists in the hash map, and if it exists, we can get the mapping from the hash map will contain the mapping between the key and the node. So in this case, we will have, let's just say, for example, we are searching for the node with the key 1, so we'll return the corresponding node, and we will get the reference to that node using the hash map. Then again, we can remove it. We can remove that node and add it to the head to make it like the most recently used element, and we will just return the node's value, because we will have it recorded inside each node. Each node will contain the key and value pair. We need to have the key as well, because when we are removing the least recently used element, we need to have the key to remove that key from the hash map. So basically, to remove the last recently used element, we know that tail prev is pointing to it. The previous element of the tail basically represents the last element that we have used. So if we have the tail preview key, we know that's the key of that node, and we can use this key to remove that element from the map as well, and also decrease the number of nodes that we have in our hash map and also in our linked list. So because there is constant time complexity required for the operations on the linked list and also on the hash map, we will, for both get and put, we will have on average constant time complexity even during the eviction of the elements if the capacity, if the number of nodes is over the capacity. And for the space complexity, we will basically just have C elements. It will be proportional to the C, where C is basically the capacity. That's the maximum number that we can have both in the linked list, that the number of nodes that we can have, and also the number of elements inside the hash map. To create the double linked list, we will create our custom class list node, which will contain the references to previous and next list node in the double linked list that we have, and also the value and the key pair that we will store in this node. We'll also have this constructor where basically we are passing the value of the list node, assigning it to the val field, and also putting the references for the next and previous list node to null. Then we will have our fields for the tracking purposes. We'll have the capacity, which will initialize by the constructor, the number of nodes in the both linked list, and also the hash map, the mapping from the key to the corresponding node holding that key value pair, and also the head and tail artificial two dummy nodes in the linked list that will help us to do operation on the linked list. Now, to do the operational linked list, we will have basically two functions. The first function will be called remove node. It will take only one parameter as the input, and basically that's the node that we want to remove. And to remove the node in the double linked list, we'll just use the previous and the next relation that we have for the current node. So we will use the previous linked list node and change its next relation to point to the node after our node that we want to remove. And then we will use the next relation of the current node, basically to point to the element after our node, and change its previous relation to not point anymore to our node the node that we are removing, but to point to the node before it. And to do that, we just use the node prev reference. Then we also will have the add to the head function, which will basically just take the node and put it at the head of the linked list. To do that, we will just point our node next to whatever node head is currently pointing. Basically, that's our artificial head. So head next will be the actual head of the linked list, the first element in the double linked list. But that element will, after the addition of this current node to the head, it will become the second one actually. So node next will be pointing to that initial first element. Then we also have to create the previous relation, and to do that, head is still pointing to the initial first element, so we can use head next to get to that element, and then we use the previous relation to point to our current node. Then we redirect our head next to point to the new head of the linked list, which is basically our node, and we still have to keep the reference to this dummy head artificial node, and to do that, we will just use the node prev to point to our artificial head. Now we finally come to the constructor of the least recently used cache. I will just initialize our capacity and the number of nodes to 0. We will create a new hash map and also initialize the head and tail to new nodes and also connect them. Head next will be pointing to the tail, and tail previous will be pointing to the first element, which is basically this artificial head. Now, when it comes to the functions, get and put. For get, we will first check if we have a key inside our hash map. If we don't have a key, the hash map will return false, or in this case, null, and then we can just return -1 because there is no key in that corresponds to the key passed by as the input to the get function. But if we have a key that matches the key passed as a parameter, we will get the corresponding node holding that key in the linked list. And to do that, we'll just use the mapping that we have in the hash map. We'll just propagate the key that we receive as the parameter and get basically the reference to our node. Then we have to remove the node and add it back again to the head. And we are using our two functions to do that. We are doing that because we want to mark this node as the most recently used one. So if we, for example, in the next iteration call, add a new key value pair, we don't want to evict this element because it was recently used. Then finally, we will just return the node value stored in the node that we received using our hash map. Next, for the put function, we will first check if the node already exists, and we will use the get therefore to basically get the null if it doesn't exist. And if the node is not null, then basically we have this key already in our hash map and in the linked list. So we just remove that node, we update its value, and we add it to the head, so we can mark it that it's been recently used. However, if we don't have the node with the corresponding key, we have to create a new node, and we will also basically assign both the value and the key, and we will add it to the head. Also, because it's a new key value pair that we didn't have before, we have to increase the number of nodes that we have, and we also have to put the corresponding mapping between the key and the node to our hash map. Then for each call of the put function, we will check if the number of nodes is larger than the capacity. And in that case, we are evicting the least recently used node. And that node is basically just a node before our artificial tail. So we can use tail prev to get that node. And then once we get the reference to that node, we can get its key. Because in the map we have the keys are corresponding to basically the key that we are storing in the nodes, not the nodes in themselves. So we are using the key of the node once we get it's referenced by TL prev, and then we remove it from the map. Then we also have to remove it from the linked list. To do that, we are just using the remove node, and we are again getting the reference to that node that we want to remove by using the tail prev. Again, because we just removed the node, we also have to decrement the number of nodes that we have in our linked list and also in the hash map. One slight note here is that we didn't really have to use the number of nodes just for the readability purposes, because we can always get the exact number of nodes that we have using the hash map, because the number of elements inside the hash map will correspond to the number of nodes that we have in the linked list.